All right. Good evening, everyone. Uh, this is Celso Batalha, Astronomy 10, Evergreen Valley College. And this is our first chat room, and I will try to show a few things in case you haven't notes yet in the course. I would like to show some few things and also to talk about the first chapter in our book that has to do with a description of what is going on in the universe, what type of stuff we might be prompt to find as we advance in our understanding of the things in the universe and how exactly the universe operates. This chat room is supposed to be informal, is not necessarily a lecture, although I will lecture sometimes. Sometimes I will go to the end of the chapter book and discuss some of the questions. Again, in midterms, I might target some of them and bring them to your appreciation. Um, and so today I will still would like to show basic things you need to do in order to be successful in this course. To begin with, you have to find the course, and by now I think you know where it is because you are listening to this communication. So once you find the course and you log in there, in the module section, you have discussions going on, and as I comment in the discussion in the orientation, face-to-face orientation, this week, closing on February 5th, you have to just make a simple description. What are your preferences? Why did you choose this class? And I can see that several students already post some information, they introduce themselves, and I will have a fun time reading all of that and making some comments tomorrow, basically. That's the first thing you should be able to do. If it's not exactly, not for this particular discussion, which is just general, but when we start to be more particularly, I would like to have you working a little bit more in depth in what you post because I will give the highest score once the post is completed. So here is one discussion that is done with the group or with the entire class. And there is another one that is going to take a little bit more of your time, and that requires the installation of a software, Stellarium, which I will use in this course a lot. And this one-on-one discussion is not for the group, it's between you and the professor. So you basically is going to be interacting with me alone, and the rest of the class will not have awareness of what the discussion goes. But basically, you go to a web page, you download the latest version, and what you need to do is just to say, hey, in February 15 at 9 p.m., what's the brightest star in the sky crossing the meridian, and you must upload a picture. By doing that, I would like to see if you have all the equipment needed and all the hardware needed and software needed to do this type of things and upload taking a screenshot or or doing such a way that I can follow your progress. Remember, this is an online class. You're not going to be seeing me to show a picture or to show your work or submit a report, handed and put it on top of my table. So you have to be able to communicate with me by submitting assessments or assignments or reports in a way that I can grade them properly. And pictures are important, especially for astronomy. Um, so this is also closing on February 12. So it's given here, February 5th. So make sure you start putting some attention on it. You might not be able to do this type of assignment at the last moment. That's what I'm trying to do. So these two discussions are important that you try to work on it every day a little bit. You get home, get 1 hour, get some of it done. I would now go straight to the textbook and find your time to check the information you need to read in chapter one. So read chapter one, Science in the Universe, a brief two, and I will go over this slide in a second. It's the first basically chapter we are reading in our book OpenStax, and let me show what I mean by that. So if you go to OpenStax and pull up the book, and this book is also in Google Books, right, Rick? I think
correct.
Yeah. So you can read it in your mobile phone. But if you choose not to read through Canvas, but to read the entire file, let me show you something interesting. You can go to the last section in a chapter, and that will give you some overview of the chapter itself. So just to get an idea of what the chapter is all about, some students feel more comfortable in having that overview, which is not that big, at least gives you in perspective what it's all about, what that chapter is all about. And if you keep following, it gives questions. I didn't find in chapter 1, but if you go to chapter 2 and you do the same exercise, you go to the end of chapter 2. Let me go. Sorry if I'm doing too fast. There you go. So when you hit the end of chapter 2, besides the summary, right? Besides the summary of that chapter, you have key terms. And again, I might have questions on midterm taking directly from there. What is an ecliptic? What is a geocentric? What is heliocentric? That is pretty much key terms in chapter 2, which we will be dealing next week. You have your summary, as I mentioned. And questions, right? Simple question, tough questions. Is the eclipse the same thing as celestial equator? Explain. So there are things that are a little bit more detailed, some other things that are more general, but anyway, it's a good resource for your dealing with the book. That's what I would recommend. I would recommend to open a chapter instead of a reading in development right away. I would take a summary of it and then go to the beginning of chapter itself and then try to explore the key terms that are given towards the end. And by doing so, I think you would be more, at least having a better overview of what the chapter is all about. So chapter 1 is pretty much a tour through the universe, not just a tour through the solar system. What the solar system, which means our star, the sun, and the planets and satellites, what are they and how far they are. I mean, this is important, but the solar system is just a speckle, little dust in the middle of an ocean, or it's just nothing. And the point of this chapter 1 is to show how, in perspective, how minute, how small we are, how spaced things are, and to get a sense of proportion of how our planet Earth, although we think it's so big, how it is in respect to the rest of the solar system, and how the solar system stands in respect to the galaxy, and how our Milky Way galaxy stands in respect to everything else. So let me browse through the pictures itself. This is a picture of two galaxies, and so you have a galaxy to the left-hand side and a galaxy to the right-hand side. They both seem to be elliptical spiral galaxies. We are going to learn these different things towards the end of the course. But here, this picture, just in this picture, is giving you some incredible information of what's going on in the universe in large scale. Think about our sun. More than that, think about 300 billion stars, billion. Not 10 stars like the sun, not 100,000, not 100,000, not a million, but billions. So 1,000 million stars, 300 billion stars. And that is the population that a galaxy such as this spiral galaxy might harbor, might have. And here you have two of them interacting. And we are going to learn in chapter 3 that what governs these interactions are gravity force. So there are four basic forces in the universe that glue and allow things to be the way they are. And these four forces we are going to explore more in detail in chapter 3. Gravity is one of them. So gravity is a force responsible for holding together planets to the sun, for holding together the Earth to the moon, for holding together things here on Earth's surface. And gravity, as you can see, is a force that can act in large scale, in a scale of galaxies, which is incredibly large. But not only that, the universe is very dynamic. It shows how these two majestic, complex systems interact. They are not far apart without interaction. They interact. In this case, they merge and they transform themselves. Now, from the very big, let's go to a smaller thing, which is, in comparison with us, is very big. It's the planet Mars. So you look at this image of Mars, and you have a crack right and through the middle of planet, which is one of these landscapes so common, not so common, I mean, but so striking in Mars surface. So Mars has canyons, and we are going to see how these canyons came to be formed. It's not a theoretical thing. It's based on observations, and it's based on the knowledge on how geology operates here on Earth, and we apply this knowledge to bodies in our solar system. We can explore and we can collect samples and visit and all of that. Now, here's a different picture. It's a picture of another type of object called stellar corpse. What that is? Well, this picture is a picture of a star, was originally a star, that exploded in a phenomenon we call supernova. It's a major release of energy in a short amount of time, and when this explosion takes place, since the amount of energy involved in the process is so magnificent, that is enough to create a whole series of atoms. And if you look around the place you are, most of the atoms you have around, with exception of perhaps hydrogen, it had been formed in the interior part of the stars, or in process similar to the one you have in this picture. So most of the atoms in the universe are hydrogen and helium, and the rest just trace amounts. It happened not to be the case here on Earth, and we are going to learn why, but is the case in our solar system. If you take the entire mass of the solar system, the content in our solar system that includes stars and planets, the majority of atoms here is pretty much hydrogen and helium, and then everything else is just a small amount of trace amounts. But this everything else is formed in stars. So the major roles of stars in the universe is the role of producers of atoms. And these atoms are the building blocks of crystals, or building blocks of cells, if we are talking about living organism. So when you think about any living organism existing here on Earth, this is only possible because the stars existed in the past that were able to create these atoms and disperse these atoms in the interstellar medium. And then when new star systems came to be formed, they incorporate these atoms into their own systems, and here we are. And based on current evidence, we suggest that life is not some isolated phenomena here on Earth, but might be something very common and very widespread throughout the universe. But this is a picture of a gas that is being dispersed, that is in the process of mixing up with the interstellar medium, and perhaps in the future this gas will be used up to form new star systems. That's a beautiful Orion Nebula. If you happen to go to our Montgomery Hill Observatory not this coming Friday, but the Friday, no, it's this coming Friday, is that correct?
No, it's also the
12th.
On the 9th.
On the 9th. Okay. So on the 9th, we have observatory, Montgomery Hill Observatory. You upload a extra credit activity. And there you might be able to see Orion Nebula with your eyes, not just to a picture. So Orion Nebula is a site of star formation. All this gas that you're seeing here, different from this gas that is being expanded and dispersed, the gas here and there is being contracted and heat up to form baby stars. So you have a nursery of stars spread all over this Orion Nebula, and you will be able to see that with a different perspective. It's not just a fuzziness in the sky, but is a site of star formation. Now, is astronomy scientific? Because if you learn about the scientific method, and that is a follow-up in this chapter 1, the scientific method is based on the core fact that nature, or the book of nature, is where, and I have to be careful when I use this word, is where the truth should be sick. So there is nothing more powerful and more self-spoken, if I could say like that, than nature itself. So we don't interpret nature. Nature reveals itself. And what a scientists do is to develop technology that enable them to read the book of nature. And by reading, we can read with very good glasses, or we can read with bad or undeveloped oh boy. Wait a second, I apologize for that. There you go. So I think I was reading the book of nature. No, I was not. But we use technology to interpret, to see what nature is showing, and then that's what scientists do. We observe nature, we try to find patterns, and we try to interpret what are the causes underlying this pattern, why things behave the way they do. And in doing so, laboratory is very important. I mean, we bring things to the laboratory, we dissect, we use our senses to, like we did in the past a lot. Now we use not our senses, but extensions of our sensors. Microscopes, for instance, we use technology, we use robotic, and as a way to dissect and to open up and to know more. Now, how can we do the same in astronomy if the object being studied is so far away? We haven't reached them yet. We haven't touched them yet. We haven't gone out of our shell in the solar system. So, how can we say so much? How can we claim that we understand how processes operate in the universe if we haven't gone there yet? Well, the answer to this question is haven't gone there, but light that has interact with all these objects, and sometimes light that has been produced by all these objects, have been traveling steadily towards us. And we, astronomers, have telescopes that collect this light and transfer that light, funnel that light to detectors. These detectors record light in such a way that resembles a book with symbols that students of astronomy can decipher, can read, and can make sense. The universe makes sense. The universe is not a chaotic. Perhaps we make our life sometimes chaotic, but the universe is not, is ruled by laws, and in science we attempt to unveil these laws and use these laws to create theories, and these theories give a better understanding on how things operate, and we use them to make predictions, and we get money to build technology to confirm or not the predictions, and that's how science pretty much operates. So here is a picture of a space telescope. Some light, as I mentioned, does not travel through our atmosphere, get dispersed. And then astronomers, what they do, they take the telescope up to space, and then you can eliminate the shielding process caused by our atmosphere. Scale. In chapter one, and I guess you are going to see this a lot. We learn a lot about sizes by checking or comparing them in a scale that we can comprehend. For instance, I can mention to you light years, as the book does, and you have to read that, or parsec, or astronomical unit. So astronomical unit is the average distance of Earth to the Sun. Light years is the distance covered by light in 1 year. Parsec is 3.2, about 3.2 light years. Is a unit that has to do with triangulations and angles in space. So astronomers use these units of distance, but when we mention light years, 100,000 light years is the size of our galaxy. It does not make sense, right? Because our brains do not work with that. But our brains understand inches and miles and kilometers, maybe, if you like more, you are used to the metric system. And so, but we don't use inches and miles to describe distance between planets or the distance among stars. Inches is not a good unit of distance. So what we do, especially in an introductory course such as this, is to use a scale, because we can think about distance if we reduce and shrink their scales. So one example, which I was discussing this with my lab students this morning. Um, and this is given right here. So we have the moon right there, and you have the Earth in scale, right? So the moon is about 30 Earth diameters apart. So you understand the size of Earth more or less because perhaps you took an airplane and you know how long it takes the airplane traveling with the speed you know to cover a certain distance. So wow, Earth is very big. So take 30 Earth, put one on side of the other, and then at the end of it, you might have a moon there, sitting there, a quarter of size of Earth. Right. So that we can understand. We can, in a room, we can kind of make a sense. Wow, now I know why eclipses, which is going to happen in a few days, why eclipses are not so common. Because any small deviation of the moon from the ecliptic plane, and you are going to learn these terms, a small deviation will take the moon out of the path of eclipse. Okay. Another one that I mentioned in the class this morning is the sun is a gigantic thing. If you think about the sun, it's 100 times as big as our planet Earth. So planet Earth is big. Think about the sun, it's 100 times bigger, right, in diameter. So if you take the sun, which is a big thing, and then you shrink to the size of a pinhead, right, which is not an inch, is a tenth of an inch? No, it's much less than that. Is 1 millimeter, perhaps fractions of millimeters, a pinhead. So if you shrink the sun to that size, where should you place the closest star to us, which is Proxima Centauri, 4.3 light years away? Where should you place it? Well, if you do the math, if you shrink the sun to the size of a pinhead, the star next to us is going to be another pinhead about 15 miles away. 15 miles away. So the stars that you see in the sky, they are within 3,000 light years away. Right? So they are very much close to us, and yet this distance is gigantic. So in other words, you can think we live in a basic empty space. So here are the planets and the sun in scale that gives or helps you to have a sense of the dimensions of this object. But what is not in scale is the separation, the distances among these objects, right? Because we can't fit that in a picture. And because of that, in our course, I put some videos I would like you to explore, at least to give you a better sense of scale. This is another galaxy, and globular clusters, very important because globular clusters historically helped us to determine how our galaxy is distributed and where the center of the galaxy is located. And so globular clusters are a group of stars that were formed when the galaxy itself was being formed. And again, how do we know all of that? Because we have telescopes that are able to do the trick of collecting light and send the light to detectors. Let me show you, if you go to our course, I have nice books. This book over here, Red Supergiants and Understanding Stellar Evolution, they are free books. In fact, is the first of free books in astronomy. They are being supported by the American Astronomical Society, written by astronomers, and is specialized in topics. Red Supergiant is very important as the source of certain type of heavy atoms. Understanding stellar evolution, all the process that underlies stellar evolution. We have our textbook, the OpenStax The link is right here. And then I have a lot of things that you want to explore. And I like particularly this link here on a scale of 10. See if I can. Oh, it's not allowing me. Try. Okay, I went to YouTube. For some reason, I tried to open from Canvas and it didn't. But let me show you from YouTube. It's a very nice video. So this video, if you can operate from your computer, which I'm not doing here, I pretty much is an animation. It goes from the foam of space-time itself with scales that we haven't have technology yet to detect and measure, and just keep on going. Look at this. And that is the minute things that we think build up quarks, which will build up atoms. So this is the smallest scale we can think of, 10 to minus 35. So certainly we don't have technology, or even those are conceived in theoretical physics. And then you keep multiplying this scale by a factor of 10. And you keep multiplying by scales of 10. And you keep on going. And more. And if you go to their side, there is a nice music. For some reason, it's not coming here. And I have it on, so I don't know why it's not coming. And now we get to quarks. Quarks are supposed to be subatomic particles that make up protons and neutrons. And of course, instruments haven't break that dimension yet. And then you go to the more common electrons and atoms and nucleus, and see all of these you're multiplying by a factor of 10. And then we have a wiggly gamma rays. So if I stop here, that wiggly gamma rays that we just saw passing right here, in blue, is right there. See the little wiggly thing? Is the wavelength of the most energetic type of particle or of light we know of. And then we go to the atoms. And then we have X-rays. You know X-rays, you've gone to the dentist, or you took that to check some broken bones, and you have your DNA. And now we become more related to something that we have heard before. Violet light, red light, skin cells. Look at the hair. That's a grain of salt. Coffee bean. And this video is interesting because you can stop, not here because this is a YouTube thing. You can stop, click on any of these images, and it will give you a description of what they are and why they are there. So it's a good source of research. And then keep on going. Now we are in the radio waves. Deimos is one of the satellites around Mars. And keep on growing. Now we are talking about states and satellites. That's our Earth. Sirius B is a white dwarf. And keep on going. Now we are in the realm of astronomy. Before we were in the realm of particle physics, and then we went to life, microscopical life, and then our everyday life. And now we are pretty much in astronomy, and that's what we're going to be talking about it. Things that are so far away, and the scale of 10 just keep on growing. See, the numbers in meters describing these scales are phenomenal. We don't carry them. And then it's much easier to use units such as light years, 100,000 light years, and megaparsecs and things like that. And now we are going to our local group of galaxies. And now we are pretty much going into a cluster of galaxies, and we are part of Virgo supercluster of galaxies. And then we are pretty much in the realm of what we can see, which is called observable universe. I mean, universe could be infinite, could be unbounded or bounded, we don't know. But we know of what we can observe, and this is what we can talk about it. So basically, with this, I would like to welcome you all in this course. Tomorrow, I will go straight to chapter 2 and use a software similar to Stellarium to describe and to emphasize the 3 types of motions that we are subject to: Earth rotation, Earth revolution around the Sun, and precession. So these 3 movements are responsible for the major changes that we observe in our life, or everyday life if you want. And also we would like to distinguish what rotation is and what revolution is. Both have something to do with the spinning. So rotation is when the spin is done through around a line that passes through the body you are discussing. And revolution is a spinning that goes, the body goes around a line that is outside the body that you are discussing. And we are going to see this tomorrow in tomorrow's class. Okay, so I'm sorry, it's not tomorrow, it's next week. Yeah, this week we are emphasizing chapter 1. So next Monday, I will, I apologize because I was in intercession. Intercession every day is a different section, different chapter book. So next week, it's going to be chapter 2. So this week, make sure you are comfortable with the course. Just read it, email me with any questions you might have, and then we will definitely start touching astronomy more heavily beginning next week. Okay. Good night to you all.